problem. It's a reasonable problem. It's a problem you'll be expected to be able to do. And so let's take a quick peek at it. It says here, determining the change in energy and the wavelength of an electron transition. And last class, at least at the end, I felt like I spent quite a bit of time trying to explain to you the difference between absorption and emission spectra, right? When we have absorption, that means the electron is gaining energy. And when we have emission, it's releasing energy. And so it says here, a hydrogen atom absorbs a photon of UV light. And so that's my little diagram of the electron is going to a higher energy level, okay? And it says here, it says to look at figure 7.11, it says that its electron enters the n equals 4 energy level. Now, something that I told you last class is if you look at figure 7.11, you'll see that n is equal to 1 when you have ultraviolet light. The n, the first n, or the lower transition, or the lower energy level, is n is equal to 1. So that's our n. That's going to be our n initial. Okay, so our n initial is going to be equal to 1. Our n final is 4, right? We're starting at n is equal to 1, and then it's being whoop all the way up to n is equal to 4. And of course, you pass n is equal to 2, and you pass n is equal to 3. Anyhow, I'm probably going into too much detail. But anyhow, it says just calculate the change in energy of the atom and the wavelength of the absorbed photon. And so we're going to use this equation here, which is a variation on Rydberg's equation that we talked about last class. And so I will give you, part of this equation for for your next midterm. And this is called Bohr's equation. All right, and it's laid out here that the change in energy is equal to minus 2.18 times 10 to the minus 18 joules. And then you multiply it by 1 over the final energy level squared, subtract 1 over the initial energy level squared. So let's take that formula, and I'm going to copy it. And I'm going to paste it into the next slide where I will solve the problem. So copy, and we're going to paste it over here. Paste, there we go. So there's the Bohr equation. Come on, you can do better than that, can't you? All right, there's the Bohr equation, good. And we said that our n final is equal to 4, right? That's where the electron is being promoted to after it absorbs this photon of UV light that we're trying to find the energy for. And then it's starting at n initial is going to be 1. So let's plug in some numbers here. So we have delta E is going to be equal to minus 2.18 times 10 to the minus 18 joules multiplied by 1 over 4 squared minus 1 over 1 squared. Now you can see that 1 over 16, right? So this would translate to minus 2.18 times 10 to the negative 18 joules times 1 over 16 subtract 1. So 1 over 16 subtract 1, that's going to give you a negative number. This is a negative number. So that means you take a negative multiplied by a negative, and you're going to end up with a delta E that's positive. Does that make sense? Yes, because this is absorption. So we're going to have a positive change in energy, right? Because the electron has to absorb energy in order to be promoted from n is equal to 1 to n is equal to 4. When you punch all of that into your calculator, you get this little tiny bit of energy, 2.04 times 10 to the negative 18 joules. And so that is the answer for part A. Okay, there's our answer for part A, is this little tiny amount of energy. And now it's asking us to solve for the wavelength. Now we know it's not going to lie in between 400 and, between 400 and 800 nanometers probably, because that's the visible portion of the electromagnetic spectrum. And we're talking about ultraviolet. So it should have a shorter wavelength, right? It should have a higher energy, shorter wavelength. Ultraviolet rays, right? Think they're dangerous, so they're higher in energy. And if you're like, well, Mr. Dion, how did you know higher in energy, shorter wavelength? Well, we talked about these formulae last class. We said that the speed of light is equal to the frequency, nu, multiplied by wavelength. And then I also told you that energy is equal to Planck's constant multiplied by frequency. Well, from our first equation, we can solve for frequency. Why do I keep doing that? Frequency is equal to c over lambda. And we can plug this in for our frequency. and we end up with this equation. E is equal to hc over lambda. And you can see that energy and the wavelength are inversely proportional. And that goes way back to the beginning of our lecture on Wednesday when we looked at the electromagnetic spectrum. Now all we have to do is plug some numbers into our formula. And so if we put in here energy, or sorry, I have to rearrange the formula, don't I? So I'm going to solve this for wavelength. So wavelength is equal to Planck's constant times the speed of light divided by, in this case, our energy, which is given to us right here. So we're going to plug all of that spinach into our equation. So I'm going to go back up here and say wavelength is equal to, if I can read my own writing here, 6.626 times 10 to the negative 34 joules times second. Remember, that's Planck's constant. I will give you that on your midterm, multiplied by the speed of light, this big number, 3.00 times 10 to the 8th meters per second. Remember, I'll give you that. That's a constant, the speed of light in a vacuum, divided by our energy, which we already solved for, 2.04 times 10 to the negative 18 joules. Well, looky, looky. You can see that joules and joules cancel out, as do seconds and reciprocal seconds, and I'm left over with my wavelength in meters. And when I calculate my wavelength in meters, I get 9.74 times 10 to the minus 8 meters. Now, it's more common to report ultraviolet wavelengths in nanometers, and so I could convert that into nanometers because I know that in 1 nanometer, I have 10 to the negative 9 meters. And so you can see that meters and meters will cancel out. And I've already done this math too. Well, actually, you should be able to do that in my head, shouldn't I? I end up with 97.4 nanometers. You know, and the thing is, you can ask yourself, does this make sense? You know, does this make sense? Yes, absolutely. This wavelength makes sense. It's shorter than what we can see with the naked eye. And so there you go. Looks totally reasonable to me. Give me a thumbs up if you think you could solve that, as long as I gave you, you know, the Bohr equation. And if I gave you these constants for, good, thanks, Violet. Great, thanks, Alexis. Perfect, Joel, Cruz, the whole gang, Fauchot. Okay, I'll take that. I'll take that to the bank. Perfect. Okay. All right, well, you know, this is just kind of a fun thing. It's Friday. These are some pictures of emission spectra. Well, down here, these are glass discharge tubes with different gases in them. So we have helium and neon and argon and krypton and xenon, and right, because I told you that hydrogen gave off a pinkish light. These are just showing gas discharge tubes for other gases. Okay, so these are the colors that you get from these elements. And some of you who are in a wet lab, or even if you're taking an online lab, you might have tried a flame test. And so you might think, well, I have to have some kind of fancy tube set up with electrodes, and it's going to be really expensive to observe this phenomenon. And that's not true at all. Okay, in fact, all you need is a sample of the element or even an ion of the element, and you need it to subject it to high energy. And so when you take an element like strontium, and this would come from the salt of strontium, which is Sr2+, and this comes from the salt of copper, which could be copper 2+, or copper 1 or copper 2. Anyhow, what happens is when you put those elements or those ions in a flame, which is a lot of energy, right? There's a lot of energy in a flame. What it's going to do is it's going to cause the electrons in those elements to do all those transitions, right? They're going to be absorbing, emitting, absorbing, emitting, back, forth, and back and forth and back and forth. And so what you see, the colors that you see here are a result of the emission of the electrons, right? Going from one energy level to the next. Okay, so that's what you're seeing here. And that phenomenon has been used for basically for millennia with fireworks. So when you go see a fireworks display, what they're actually doing is they're taking a salt. So they're taking a salt of, where they have a cation, like maybe copper or sodium or barium or strontium or titanium, which is white. And they're just subjecting that to a lot of energy, which comes from gunpowder or black powder, right? They set that off, and what that does is it causes all of these electronic transitions, right? Absorption, and then of course emission. And then we see the light that's emitted, and we see these different colors. Kind of cool, huh? In fact, if we focus on something like sodium, okay, you see how sodium has this kind of yellow color here? It's kind of yellowish. In fact, sodium only has two lines in its emission spectrum. And if you look, I don't know if anybody that's hearing my voice has ever done this before, but if you look at the sodium emission on like a cheap instrument for observing these kind of spectral lines, the first college I taught at, they had one where we could look at emission spectra, but they were so hard to see. You had to like imagine them. It was so crummy. But anyhow, the sodium, it basically blended together. You know, it was like one big yellow smudge. And that's the idea, right? That's why sodium lamps are yellow, is because the two lines in the emission spectrum are so darn close to each other, right? They're both pretty close to yellow anyway. And so when they mix together, you get something that's just yellow. Now, if you think, okay, well, if sodium's emitting yellow light, well, it must be absorbing all other regions of the electromagnetic spectrum. And that's perfectly reasonable. That's totally true. Okay, all right. Well, what I want to do now is switch gears. And now we're going to get into section 7.3. And I'm going to skip ahead here and just talk about this slide for a second, okay? You've probably all heard of this formula here, equals mc squared. This was invented by Albert Einstein, and a lot of people think that this is what he won the Nobel Prize for, but in fact, I explained to you that he won the Nobel Prize for the photoelectric effect. And what he said is that matter and energy are alternate forms of the same entity. Now, in our everyday lives, this seems pretty counterintuitive, right? If you think, okay, well, it's saying here that you have basically that you have energy is equal to a mass times the speed of light squared. Okay, that's cool. Now, what if I take some kind of mass? Let's say I take some wood and I burn that. Do I get some energy from it? Sure, yeah, I get some energy from it. But in my day-to-day life, I can't convert wood into pure energy, right? I'm always going to get some ashes, some gas given off, right? So again, it's kind of counterintuitive. Likewise, we don't think about converting energy into matter. And in fact, this equation really only holds true. I'm not saying that it's not true, but it only holds true down to the size of the nucleus. So it only holds true for the nucleus. Okay? Because if you think about it, if you were to take, you know, even a small amount of mass in our everyday life, that would have a crazy amount of energy because you're multiplying it by the speed of light squared. The speed of light is 3 times 10 to the 8th meters per second. So that would mean insane quantities of energy for tiny, tiny little bits of mass. And so again, this equation is only going to apply to nuclear chemistry, and that's something that we'll look at in general chemistry too. But it says here that all matter exhibits properties of both particles and waves. Okay? Electrons have a wave-like motion and therefore have only certain allowable frequencies and energies. And I'm going to go back to that guitar picture in a second to explain this. Now, you might be thinking, okay, Mr. Dion, you're off your rocker, man. How would all matter exhibit the property of waves? I'm not a wave. I'm looking down at my legs right now. I don't see any waves. I just see my legs, you know. I'm looking at my iPad. I'm not seeing a wave. Like, what are you talking about? Okay. Well, this is something that was postulated by de Broglie. And he says here that matter behaves as though it moves in a wave. And we call that the de Broglie wavelength. And for any particle, we can calculate the de Broglie wavelength. Okay. And the de Broglie wavelength is equal to Planck's constant, h. So this is, again, Planck's constant divided by its mass multiplied by its speed. Now, if we think about Planck's constant, okay, Planck's constant is 6.626 times 10 to the negative 34 joules times second. That's a really small number. So if we divide this by something with a large mass that's moving at, you know, a high speed, we're going to get some kind of wavelength that is basically so small that it's going to be just crazy small, okay? So small that it becomes irrelevant. And that's why when you're looking at your desk or yourself, that's why you don't see waves, right? You're so big that the de Broglie wavelength is negligible because you're such a big particle. No offense, okay? Where's the slide I wanted to show you? Okay. You know what? First, let's try solving this problem, okay? First, let's just try solving this problem. So here's our equation for the de Broglie wavelength. I'm going to kind of jump around here a little bit, you guys. It's a Friday. Come on, bear with me. So we have this right here. So that means we can calculate the wavelength for anything. And you're like, well, can I calculate my wavelength? Sure you can. Sure you can if you really want to. But first, I want to first talk about determining the wavelength of an electron. Okay, so let's get down to electrons. And don't worry, I'm going to come back and make full circle and make it the whole story about this, okay? All right. So it says here, find the de Broglie wavelength of an electron with a speed of 1 × 10⁶ meters per second. So that's, you know, that's only, what, 100 times less than the speed of light, roughly, and the mass of an electron, and we have Planck's constant. So we have everything that we need. We literally just have to plug everything into the formula. Give it a try, you know, or you can follow along with me, but I would recommend giving everything a shot in this class. 6.626 times 10 to the negative 34 joules times seconds. And we're going to multiply that by the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. We're going to multiply that by the speed of the electron, which is 1.00 times 10 to the 6th meters per second. Oops, didn't mean to do that. Meters per second. And we're going to find the wavelength of this electron and see what kind of wavelength it's got. So we see here that we have our kilogram meters per second squared. Good. So we're going to end up with, we have, you know what, kilogram meters per. So let me just work out the units. Do you guys know that a joule is equal to a kilogram meter squared per second squared? Does everybody know that? Has anybody ever seen this conversion factor before? I don't know if I've even mentioned it in class, that a joule is equal to a kilogram meter squared per second squared. Has anybody seen this in physics before? Okay, Violet, one person has. Yeah, Violet says, I took physics, okay? So that's why you know that. And then Alexis says, yeah, so if we take that, right, if we take this and we multiply it by a second, right, which is what we're doing right here. I just want to walk you through the units is all, okay? I don't want somebody to be like, where's he getting these numbers from, okay? Where's he getting these units from, Mr. Dion? You know, you're going, where are you getting this stuff? So if we multiply this, right, we remove the second squared, so we have kilograms times meters squared per second. So that would be the unit that you would have there. And now you can see why kilograms cancel out, okay, seconds cancel out, and meters cancel out, and I'm left over with meters, okay? I just wanted to show you those units. It's always nice to make sure that our units cancel out. And we end up with this wavelength, which is 7.27 times 10 to the negative 10 meters. Now, if I convert that into nanometers, and we did that earlier on today, so 10 to the negative 9 nanometers, or sorry, meters in 1 nanometer, like that. Meters and meters cancel out. We end up with the number of nanometers. We end up with this, which is 0.727 nanometers. Okay? Anyhow, the idea is this, is that this wavelength, okay, this wavelength is actually pretty close to the size of an electron. Okay? And I want you to keep that in your hat, okay? Just take my word for it that this wavelength is pretty close to the actual size of what an electron is, because that's going to be important when we get to this slide right here. Okay, this one right here. So this one shows you de Broglie wavelength. So remember, the de Broglie wavelength is equal to Planck's constant divided by the mass multiplied by the speed. Okay, so we got a bunch of different substances here. We've got electrons, we got a baseball, and Earth. We'll worry about the other ones another day. But anyhow, you're going to have to listen to me carefully here, okay? And this is actually just kind of a fun thing, okay? So if we have an electron, it's got this little tiny mass, and it's got this little wavelength. Well, that wavelength, okay, of this fast-moving electron is actually very close to, so this wavelength here is actually very close to the size of the electron. And so the only time, pay attention very carefully here. I know I sound like a dad, okay? But just bear with me. I am a dad, okay? The only time that we have to really consider the de Broglie wavelength, so both the fact that something has mass and a wavelength, the only time we have to do that is when the size of the substance and the wavelength are similar. Okay? So pay attention, like listen to that carefully. Because the wavelength of that fast-moving electron, where I have that little blue star next to, because that is close to the size of an electron, that is why we have to consider that sometimes that an electron, we treat it like it's a particle, like it's a substance, right, that has mass, and sometimes we treat it as if it's a wave. The reason why, if we take something like a baseball, okay, a baseball is about 10 centimeters, wide, maybe. If we calculate, so that's 0.1 meters, okay? If we calculate the de Broglie wavelength of a baseball moving at 40 meters per second, so that's a pitch, the speed of a pitch maybe, okay? It's got this wavelength here. Now, this is something that I never thought about until I taught this class as a teacher, many years ago. As a student said, well, what's the big deal about that wavelength? I'm telling you that wavelength is so small that you can't detect it. Okay, 10 to the negative 34, too small to be detected. Okay, 10 to the negative 10, yes, that can be detected, but 10 to the negative 34, too small. So that is why when you throw a baseball or you look at a baseball, you don't see a wave. Okay, you just see the particle. Now you got an example here that's just beyond insane. Okay, the planet Earth, here's the mass in grams, here's the speed, and you have a wavelength that is just so crazy small. I mean, there's no hope of ever detecting that wavelength. Uh-oh, sorry. My father's trying to call me. I guess I will hang up. Bad timing, Dad. Where was I? Share my screen. Sorry about that. Okay, where's my slides? Oops, what happened there? Oh, shudder. Can you see my slides? Okay, thanks, Joel. Thanks, Emma. Perfect. Good. Thank you. Okay. Sorry about that. Good gravy. Is this some kind of joke? That was my brother. Okay. Sorry, you guys. Go to application. Share screen. Okay. Go. Can you see my screen again? Sorry about this. I apologize. Okay. Thanks, Brittany. Thanks, Alexis. By the way, thank you for coming to class and actually listening to what I'm saying. If I was to ask, can you guys see it? And then I get nothing, that would be pretty discouraging. Anyhow, I just give me a thumbs up if you follow what I'm saying, that when you have an object that's too big, I know I'm talking about it a lot, but I find it really interesting. So I'm like everybody else in the world. I tend to talk more about the things that I find really fascinating. Everybody does it. Okay. It's not just me. So, I want to switch gears again, and I know I'm doing that quite a bit here, and I'm going to come back to this for a second, but I want to go back to that guitar string page, okay, and talk about why electrons only have certain energy levels. And basically, what de Broglie, the reason, or if you're wondering, like, where did that equation come from, Mr. Dion? You just kind of magically sprung this equation on me. Lambda is equal to h over mass times speed. Well, where he came up with that equation is he said, okay, well, if waves can have the property of a particle, maybe a particle like an electron can have the property of a wave. So that's basically how he, came up with the equation. He started with that assumption, okay? And then he said, well, why does an atom have fixed energy levels, like in the Bohr atom? Because if you remember Bohr, that was the classic example of somebody massaging an equation to basically fit the data. So he thought about, okay, well, what if you have the wave motion of something like a guitar string that only has certain allowed energy levels, okay? So if you have a guitar string, and some of you are probably musicians, and you were to pluck that string, there are only certain wavelengths that are allowed, okay? And if you pluck the guitar string, you don't just get like some kind of random motion. You get this beautiful harmonic, perfect up and down motion here, which shows you the wavelength of the string. Now, if you were to put your finger maybe somewhere in the middle here of the guitar string, it makes what's called a harmonic, okay? So you basically cut that wavelength in half like that, You end up with 2 half wavelengths, okay? And then it's going to make a sweet sound. But what happens if you're to move your finger just off of that center position? It's going to make a horrible sound or maybe no sound. And the reason why is because you don't form that standing wave, okay? It's not perfectly balanced. You don't get that perfect standing wave. And so basically what de Broglie said, and the reason he came up with that equation is he said maybe electrons in their orbits behave the same way, right? He said maybe they can only have certain allowed energy levels, because if you think of the same thing, if you think of an electron moving around in its orbit, if you have, its orbit, as a whole quantum, or as a whole, as a whole quantum number, as a whole integer, n is equal to 5, 3, 2, 1, whatever, okay, all the way up to infinity. If you have a fraction, you're not going to have a standing wave. You're actually going to cancel the wave out. And so that is where he came up with that equation from. Okay. I'm not going to ask you to write me an essay about it or explain the guitar string to me or anything, but I think it's kind of cool. It's very cool that he was able to make that connection. He said, well, maybe if this happens, if in the real life, or sorry, at the macroscopic scale, we can have a standing wave, but if we cancel the wave out, yeah, somebody says, I actually think it's cool. It is cool. Okay. Hey, I'm cool. I'm cool. I might not be as cool as you guys, but I'm still cool. And I think that that's really cool. So again, de Broglie proposed that if energy is particle-like, then perhaps matter is wave-like. And that's how we, really start to explain why if electrons have wave-like motion in orbits of fixed radii, they would only have those certain allowable energies and frequencies. Anyhow, I know I'm kind of rambling on about that, but I think it's really interesting, and I think that's really cool. Come on, you gotta bear with me. We got to do one more slide on this, okay? And if you think, okay, well, come on. If you said, Mr. Dion, that an electron can be either a particle or be thought of as a particle or a wave, well, waves have diffraction patterns. Remember that? Remember when we talked about diffraction patterns on Wednesday? Well, if you take X-rays and you shine them at aluminum, okay, you'll see that most of aluminum is empty space, right? And we talked about how most of the atom is empty space earlier on, and then you have nuclei. Well, if you shine X-rays through aluminum, some of them are going to go through and you end up with a diffraction pattern. So that's what's shown right here, is a beautiful diffraction pattern. But check this out. So X-rays, and I just want to make sure you're with me, X-rays are waves, right? These are waves, electromagnetic radiation. Electrons, now I told you, and I admit this, at the beginning of the class, I was like, an electron is a particle, has a mass, right? 9 times 10 to the minus 31 kilograms. And you were like, yay, thank you, Mr. Dia. Okay, anyhow, but now I want you to think about electrons. What these guys did is they took a beam of electrons and they shone it at aluminum, and they also got a diffraction pattern. Is that crazy or what? Okay. And the only reason they get a diffraction pattern is because the size of the holes, basically, that the electrons went through the aluminum, were about the size of the electrons. And so it was diffracted like a wave. Is that crazy or what? Who's with me? Just need to take a quick break here. Okay, nobody's with me. Anyhow, all right, maybe I should keep moving here. I think the diffraction pattern is really cool. Somebody says kinda. All right, anyhow, so there we go. Let's see here. So the conclusion is that electrons, which are particles with mass and charge, can create patterns just as electromagnetic waves do. Hey, you guys, I admit it's not intuitive, right? It is not intuitive. But anyhow, and we could spend quite a bit of time on this slide here. As somebody said, this is probably the most intelligent picture ever taken in history. I'll just say a couple of quick things about this, and you could spend some time. This is kind of a summary of what we've talked about so far in Chapter 7, going from black body radiation all the way up to the Bohr model and then de Broglie. And we're going to move beyond that. We're going to talk about the Schrodinger equation in a second. But if you look at this picture here, the Solvay conference, I need a new prescription really bad, so I can't read the names on here. But you can see that you got Einstein here. And you can see Madame Curie is here, so Marie Curie is there. Anyhow, Heisenberg is in there. Anyhow, so a lot of these, very intelligent scientists are in here. Something that I'll just say about this before we move on, something I'll say about this picture is, a lot of these scientists, they had time. You know, they really had time to sit and think. Some of these guys only published maybe 1, 2, 3 papers. Like I have more scientific publications than a lot of the people in this picture. Now, mine aren't nearly as good. Mine aren't nearly as cool. But I always think like, you know what these guys had is they had time. They really had the time to sit, you know, and think about things. And I think that that's really cool. Anyhow, that's just kind of probably partially my opinion. Anyhow, let's move on and talk about something called Heisenberg's uncertainty principle. And if you've ever watched the Breaking Bad show, the chemistry is really good in that show. You've probably heard of Heisenberg. And Heisenberg came up with this uncertainty principle. And he says this, he said, if you have a particle, like an electron, right? If you have a particle that has a definite location at any instant, right, like a baseball, it's a particle. You can see where the baseball is here, okay? Whereas a wave, you can't say, well, there's the wave. You know, a wave is spread out through space, okay? But he says, then, if an electron has both the properties of a particle and a wave, can we actually know where it is? Is it actually going to be like it was in that Bohr model, right, where you have the nucleus and you have n is equal to, is it really going to be like just going around in orbits like that? That's a horrible picture, so I'll delete that. But is it really going to be like that? Oh, we're really getting into interesting stuff now. Well, Heisenberg's uncertainty principle states that it's actually not possible to know both the position and the momentum of a moving particle at the same time. And so the more accurately that we know the speed of something, the less accurately we know the position and vice versa. Let me unpack this equation for you here, okay? So delta x, the delta stands for the uncertainty in the position. Momentum is actually equal to mass times the velocity, okay? So mass times speed. Now mass is definite. Mass isn't going to change, but there's uncertainty in the speed, okay? So there's uncertainty here in the speed. And again, when we take mass times speed, we get the momentum. And momentum has a vector, okay? There's a vector to momentum. And if you're like, oh, Mr. Dion, what are you rambling on about? Well, all you really need to know is that if you take the product of the uncertainty in position and multiply it by mass times the uncertainty in speed, it has to be greater than or equal to Planck's constant divided by 4 pi. Now, Planck's constant is a very small number, right? A very, very small number. And so we're going to be talking about particles with really small masses, like an electron, okay? Now, this picture here, this is actually an experiment. It's not a figure from our textbook. This is an experiment done by Dr. Diaz, and it's actually kind of hard to tell what's going on in this, in my opinion, but what he did is he took 2 razor blades and put them close together with a pair of pliers so that he made a little slit like this, okay? And then he took a wave from a laser pointer and he shined that wave through the slit. Maybe I should use green, okay? So he shined that wave through the slit. And basically, as you go from here, maybe I should use a different color here. As you go from here to here, the slit is getting narrower. So narrower slit, okay? And what he's saying here is that the narrower and narrower that you make this slit, the more certainty you know the position of the wave that's going through, okay? And again, we can think of electromagnetic radiation, the laser beam, as being a particle, right? Okay? And so the more certainty that we know where the particle is passing through, as we make the slit narrower and narrower, you can see that it spreads out more and more. It's kind of hard to tell unless you're looking at it really closely, but it does spread out more and more. Anyhow, it's a common experiment. You can see people doing it on YouTube and stuff. And so the matter wave of the electron occupies space near the nucleus and is continuously influenced by it. And so what we're going to do now, based off of the Heisenberg uncertainty principle, we can't know for certain, like we did with the Bohr model, n is equal to 1, we have an electron orbiting around, and n is equal to 1, n is equal to 2. We're going to see that we have a more accurate representation of the atom, and that comes from Schrödinger, okay, who is an Austrian scientist, and he developed what is called the Schrödinger wave equation, and it allows us to solve for the energy states associated with the particular atomic orbital. Now notice that before we talked about orbits, right? Bohr's model had orbits. Now we're talking about orbitals, which is just a variation on orbits, and I'll explain what orbitals are as we move along. And Schrodinger developed this equation here, which when you look at it, looks pretty simple. You have, this is called a Hamiltonian operator. You have that multiplied by psi is equal to energy times psi. You're like, that's pretty simple. Well, the problem with this equation is that this Hamiltonian operator, just this little part here, is represented by all of this. And if you're like, why, what are we talking about, Mr. D? Why are we doing this? Okay, the reason why is because the de Broglie equation and the Rydberg equation for the energy levels of an atom, the reason we're into all of this is because that only works for hydrogen. Once you get to helium, it didn't work at all. It was horrible. And then once you get to lithium, I mean, it's no good at all. It's pretty much useless. And so Schrodinger allowed us to solve for the energy states of any electron in any atom. Now, it's not perfect, but it's a pretty darn good approximation. And so the actual, this is called the wave equation here, this psi. The wave equation is actually meaningless, but if you square that wave equation, you get what's called a wave function. So psi squared is the wave function. And of course, I'm never going to ask you to solve any of this. Okay, it gives you the probability density or the measure of probability of finding an electron of a particular energy in a particular region of the atom. And if you're like, I am not sure what you're talking about, well, let me speed up and I'll get to something that's even simpler. So if we take the wave equation, okay, and we plot the wave equation in this axis here, the x-axis is a function of distance from the nucleus, okay? I told you that it's meaningless, okay? This doesn't have any meaning, but if we square it, then it gives us the probability density of where we would find an electron from the nucleus. So it says here, the probability of finding a particle between A and B is given by the area under the shaded curve. So if we look between these two distances away from the nucleus, you can see that we have regions with higher probability. This is actually the region with the highest probability of finding electron. And we have actually regions where there's no probability of finding electron. Now, in order for us to find a way to describe the energy levels of the electrons in that wave function, we use what are called quantum numbers. So if you're kind of lost in the last like 6 minutes of my lecturing, you can take a deep breath right now and kind of sigh a breath of relief, because I'm not going to ask you to ever solve a differential equation like that never in this class, because you don't need calculus to take this class. Okay? And we're going to talk about what are quantum numbers. And quantum numbers are numbers that we can use to describe the energy and the position and other properties of electrons that are in atomic orbitals. So if you're not completely sure about where we are, take a deep breath, and I promise you're going to understand. Give me 5-10 minutes and you'll know where we are, okay? So an atomic orbital, so that probability of where we find an electron in an atom, and atoms besides the hydrogen atom, it'll work for the hydrogen atom as well, but for any atom on the periodic table now, okay? We're going to use 3 what are called quantum numbers. And I asked you to read this before coming to class today, and I hope you did. We're going to use what's called the principal quantum number. And that number we represent with the variable n, and that has to be a positive integer. What's a positive integer? 1, 2, 3, 4, so on and so forth. It says here the value of n. What does the principal quantum number mean? It means the relative, or it indicates the relative size of the orbital, and therefore its relative distance from the nucleus. So as we go from n is equal to 1 to 2 to 3 to 4, we're getting bigger and bigger and bigger orbitals. Okay, the size is getting bigger and bigger and bigger, and therefore the orbitals are getting farther and farther and farther away from the nucleus. Okay, so that's the first one. The second one is L. L. And L is called the angular momentum quantum number, and it is also an integer, except now we can go from 0 all the way up to n-1. So you're going to have that memorized. And what L represents is it indicates the shape of the orbital. So does the orbital look like a sphere? And if you did the Learn Smart, you would have learned that you have orbitals that look like spheres. You have other ones that look like dumbbells or something like that. Maybe you're like, maybe I don't look like that. A dumbbell doesn't look like that. Maybe it looks like a propeller to you. We have other orbitals that have even more exotic shapes like this. So you kind of have 2 dumbbells. Like that looks like a butterfly, Mr. Dion. Anyhow, I'm trying my best here to draw. Anyhow, but that's what the angular momentum quantum number means. is it represents the shape of the orbital. Then we have ML, which is the magnetic quantum number. That can have values of -L all the way up to positive L, and that indicates the orientation. Let me give you some examples here, okay? Let's say you had, I'll use the red pen, okay? And I'm just going to kind of walk you through this slowly here. If you have n is equal to 1, what would your values of L be? Well, the only value that you could have for L would be 0, because L goes from 0 all the way up to n minus 1. What's 1 minus 1? It's 0. So you literally have one value of L. What would your values of ML be? Well, M can be minus L all the way up to positive L. There's no such thing as -0 and +0. And so ML could only be 0. Give me a thumbs up if you follow me on that. You're like, at least I think I could solve this formula, Mr. Dion. Okay, cool. Thanks, Kenner. Perfect. Okay, good. All right. Well, if you follow me on that, then the rest won't be much of a stretch, okay? If we had a quantum number of n is equal to 2, and I'll walk you through this one as well. If we had n is equal to 2, what would our L be? Remember, the L can be 0 all the way up to n minus 1. And so it can be 0 and it can be 1, right? It can't be 2 because 1 or 2 minus 1 is 1. And then what can my values of ML be? Well, ML can be minus L all the way up to 0 and all the way up to positive L. So if I have an L of 0, when my L is 0, my ML is going to be 0. And when I have an an L of 1, my ML can be -1, 0, and +1. Give me a thumbs up if you follow me on that. All right, thanks, Matt. Yeah, it does make a lot more sense. I agree. The theory it's a little tough. It's a little tough. Don't worry, Mr. Dion's never going to tell you, oh, that's easy, you guys. He would never do that. No, not in this lifetime, okay? Not in this lifetime, okay? And now you could do the same exercise for when n is equal to 3, okay? You can do the exact same exercise for n is equal to 3. And if you're, if you're not in the same place that, Matt is, where Matt's like, yeah, it makes sense to me. You know what? One of the best ways, who is with me? One of the best ways to clear up misunderstandings in chemistry is to practice. I find that is how I do some of my best learning in life. Yeah, Kenner says, yes, I agree. Some of the best learning you'll do is just done by trying a problem, seeing if you can reason your way through it, because often if you can, you understand what the heck is going on. Well, with that in mind, let's give a question a shot here. It says, what values of the angular momentum, L, and magnetic quantum numbers are allowed for a principal quantum number of 3? How many orbitals are there in this energy level? So I'm going to have to explain this to you a little bit. Anyhow, so let's start out. If we have an n is equal to 3, what are the possible values of L? Okay, our L can be equal to 0, it could be equal to 1, and it could be equal to 2. Right? I kind of put some space in there just to give me some room to work, because L is equal to 0, right? L is equal to 0 all the way up to n minus 1. And if you're like, didn't you put that on the last slide? Yes, I did. I'm just repeating myself, okay? So then, if we have an L is equal to 0, and I'm going to divide this up a little bit maybe instead of have commas here. Okay, if we have an L is equal to 0, what is our possible value of ML? ML could only equal 0. Why? Because ML is equal to minus L all the way up to 0, all the way up to positive L. When L is equal to 1, our ML can be equal to -1, 0, and +1. When L is equal to 2, our ML can be equal to -2, -1, 0, +1, and +2. Give me a thumbs up if you follow me on ML. Okay. All right, Maddie, thumb. I like it. Okay. I'm not asking you to be able to, solve every problem in the book yet. Hold on, we're getting there. We're going to get there. Okay. So what I want to tell you now is that each ML value represents an orbital. Oh, okay. Okay, I'm going to underline that or highlight that. So let's count up how many ml values we have. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, that's interesting. So we have 9 total orbitals. Okay? And if you're like, okay, well, what's the significance of all this, Mr. Dion? Like, what's your point? What's your take-home message? I can figure this out. Of course, I can use a little formula like this, and I can use that formula. Sure. You told me that n is equal to the size, L is equal to the shape, ML is equal to the orientation or the direction, okay? And then each direction represents an orbital. Okay, cool, cool. But what's the significance? Don't worry, we're going to get there, okay? I really want to bust through all this. And anyhow, I guess I put some more problems in here, didn't I? Oh, that sounds like something I might do. You know what? I think that these are slides that I put in last year to help my students out who might have been confused. So let's walk through them. Never hurts to repeat something over and over, okay? So this is just kind of vocab to walk you through some vocabulary. It says here level. The atom's energy levels or shells are given by the n value. The lower the energy level, the greater the probability that an electron is closer to the nucleus. And if you're like, well, that sounds just like the Bohr model. Yeah, it does kind of sound like it. So if I talk about a level, I'm actually talking about an n value, so which is the principal quantum number. Okay. The next one is a sublevel. Okay. A sublevel, it says the atom's levels, right? N is equal to 1, 2, 3, 4, 5, 6, whatever, are divided into what are called sublevels, or sometimes in some books they'll be called subshells. Either one works. That are given by the L value. Each L value is assigned by a letter. You have to have this memorized right here. So I'm going to put here memorize this. The L is equal to 0. When L is equal to 0, we call that an S sublevel. When L is equal to 1, we call that a P sublevel. When L is equal to 2, we have a D sublevel. And when L is equal to 3, we have an F sublevel. Okay? So SPDF. So if you have 0, 1, 2, 3, the sublevel is SPDF. And if you're like, where did those words come from? I think there's a description or an explanation for where they come from in our book. I can't remember, but you can look that up. There is a rationale for it. Basically, they started with something rational and then they gave up. Anyhow, and the next one is the orbital. And this is something that I told you in the last problem. It says each combination of NL and ML specifies the size, energy, or size or energy, the shape, and the spatial orientation of one of the atom's orbitals. We know the quantum numbers of the orbital in a sublevel from the sublevel name and the quantum number hierarchy. For example, if you have a 2s sublevel, okay, you're going to know that your n is equal to 2, right? Let's examine this carefully. I want to make sure that everybody follows me before I get too far, right? The 2 is equal to the n. The S is equal to the L. And I told you that when L is equal to 0, 1, 2, or 3, it indicates an S, P, D, or F orbital. So that tells you that the 2s, right? It tells you that your L is equal to 0, right? And if your L is equal to 0, then your ML has to be 0. All right? Let's take a look at another example. If we have a 3p sublevel, well, the 3 indicates our value of n. Our P indicates our value of L, and our value of L is equal to 1. I should have written this up here. But anyhow, our value of L is equal to 1, and it tells you that our ML, right, has to be -1, 0, and +1. So that means you have 3 orbitals in that sublevel, right? Because I told you that every ML value represents an orbital. All right. Well, let's keep on going from here. With that in mind, let's try another problem. It says here, give the name, magnetic quantum numbers, and the number of orbitals for each sublevel with the following quantum numbers. So let's just start with A. Let's not even read the whole question. Let's start right here. We'll focus on one problem, and then we'll worry about the rest at another later on. So we got N is equal to 3, and L is equal to 2. Okay? So what kind of, and it's asking us, give the name, magnetic quantum numbers, and the number of orbitals for each. So the name, who could tell me the name of this orbital? Okay, and if you're not sure what I mean by name, I'll help you out. This would be, the name would be a 3d orbital. Okay, it's a 3d orbital. Where did I get the 3 from? The 3 came from n, the principal quantum number, and the d came from the L value. Remember that when L is equal to 0, 1, 2, or 3, when it's 0, it's S. When it's 1, it's P. When it's 2, it's D. When it's 3, it's F. So if my L is equal to 2, that means that I have a 3d orbital. I have a 3d orbital. Then it's saying, give us the magnetic quantum numbers, which is the ML values. So my ML values are going to be -2, -1, 0, +1, and +2. And then it says, give me the number of orbitals. Well, each one of these represents an orbital. So I have a total of 5 orbitals. Do you want to try one more? Want to try the next one? This is a problem from the book. So the solution is in the book. Okay, let's try another one. Let's try when n is equal to 2 and L is equal to 0. Could somebody give me the name of that orbital? I just want the name. Nothing fancy. Yes, Matthew, Liv, Violet, Brianna, Amanda. Wonderful. You're making my Friday really great. You're making it, it's taking a turn for the better. It's a 2s orbital. Hot diggity darn, right? We got a 2s orbital. What are our values for ML? Well, if it's an s orbital, we've only got one value for ML, and that's 0. And so we have 1 orbital, right? Because every ML value okay, let's try another one. I want to continue with the fun here. Let's try C, and then we'll have to move on. N is equal to 5. I'm probably going too slow here for you guys. I don't know. Anyhow, can somebody tell me the name of this one? If I have N is equal to 5 and L is equal to 1. Violet says it's a 5p. I'd have to tend to agree with that. We got a 5p. For ML values, we're going to have -1, 0, and +1. So we have a total of 3 orbitals. Thanks, you guys. I really appreciate the answers. That makes my day. 3 orbitals. Okay. And if any of you, I'll just stop here for a quick second. We have, it's 10:20. We only have 2 hours left in lecture. If anybody here has ever taken high school chemistry, you've probably done electron configuration. And you know where we're going with s orbitals and p orbitals and d orbitals and f orbitals. But if you've never studied chemistry in your life, we're going to get there. And that's why we're kind of building on that. So I just want to explain to you guys that some of you have taken maybe AP chemistry and you're like, I know how to do electron configuration. Well, if somebody, and you can totally enroll in this class without any chemistry background. And so we have to kind of build that up. Okay. So just be patient. If you're like, when do we get to do the fun stuff? It's coming. Don't worry. Here's the answer. Hey, this is a good question. Here's an old chestnut. This is a classic from the ACS final. It says here, problem, what is wrong with each of the following quantum numbers? Could anybody tell me? I'm just not even helping here, am I? Could anybody tell me what's wrong with A? I'll just throw it out there to my students. There's a problem with these quantum numbers. Okay, in A, there's something wrong here. Is anybody able to figure out what's wrong? You have N is equal to 1, L is equal to 1, ML is equal to 0. Yeah, Violet. Yeah, counter says 1 can't equal 1. Yeah, absolutely, right? This is a big no-no, right, you guys? Right? L cannot equal 1 because when N is equal to 1, the only values of L are going to be 0. Okay, let's try the next one. The next one might be a bit trickier. I don't know. I haven't looked at it. I have N is equal to 4, L is equal to 3, ML is +1. I have a 4D. Oh, there's a problem here. Did anybody see the problem with this one, with B? It might not. Yes, Grant says, Grant got it. Yes, it's the name is wrong. So N can definitely be 4. N can go technically all the way up to infinity, I suppose. But anyhow, we're definitely not there yet. Yes, Aaron says that it's F. So it's not 4D. It would actually be a 4F orbital, right? Because remember, when L is equal to 0, 1, 2, or 3, we have S, P, D, F. And so since L is equal to 3, this is an F orbital. Let's try the last one. These are kind of fun. Again, I haven't looked. Oh, yeah. What's the problem with this one with C? I know it's hard to communicate via Teams, but you guys are better than me at it. Yeah, Grant says ML is wrong. I see there's a big problem with ML. ML is -2, right? That cannot be. The only possible values for ML here are ML has to be either -1, 0, or +1. So that's wrong. So what I was saying when I saw this slide and I was like, oh, this is a good one, is that ACS final, your final exam always has this question on it. Okay, some iteration of this where you look at it and you figure out which quantum numbers are incorrect. Always a problem on the ACS. And it's very doable for the students too, which is nice. Here's just a slide that shows you all of the principal energy levels, shows you their L values, their sublevel designations, the angular momentum quantum numbers, or ML. Then the number of orbitals. So what I get you guys to do so far is I said, okay, if let's just say this one here, you have these ML values. Sorry, I didn't circle all of them. So if you have these ML values, you have a total of 5. There's a faster way to calculate it, which is to use this formula right here, okay, which is 2L plus 1. So if you take 2 times 2 and you add 1, you get 5, okay? You can use that. I don't really spend a lot of time on that with my students, but if you want to use that formula, be my guest. And then for the total number of orbitals in an energy level, you square n. So if you have n is equal to 1, 1 squared is 1, and there's only one 1s orbital. If you have, like, let's say you have n is equal to 2, 2 squared is 4, right? You have the 2s orbital, you have 3 2p orbitals, right? And then so on and so forth. Anyhow, just kind of fun stuff. Anyhow, what time is it? 10:24. I'm probably going too slow, but whatever. You know, some of you are probably wondering, hey, Mr. Dion, you talked about shapes. What are the shapes of these orbitals? Well, if you read the chapter, you definitely know what the shapes of the orbitals are. And here they are. Here's some shapes of orbitals. It says here orbital shapes and quantum numbers. So an s orbital is a sphere, and you'll probably hear me just call it, it looks like a sphere. Right, and you can see that as the principal quantum number increases, what happens? The size of the sphere just gets bigger and bigger and bigger, right? So the probability of finding an electron gets further and further away from the nucleus. The next one is the p orbital. I'll be honest with you guys. Everybody calls them a dumbbell. They say it looks like a dumbbell. And you're like, well, that dumbbell looks like this to me, Mr. Dion. I don't work out with this kind of like funny shaped propeller thing. Anyhow, that's what everybody calls it. But I just want to cover the ML values, the angular momentum. It looks like a peanut. I like it. P for peanut. There we go. Good one, Gage. All right. So since we have 3 ML values, remember that ML represents direction. Okay. So you can think of the 3-dimensional axes, the X, Y, and Z axes. So that means the dumbbell could be oriented in the X direction, Y direction, or the Z direction. Then you know what, you guys, I would expect you, obviously all of our exams are multiple choice, but I would expect you to be able to draw these. Okay, everybody can draw a circle, and Gage, everybody can draw a peanut, right? Okay, well, for the d orbitals, you get some pretty cool looking orbitals here. Okay, so remember the L can be equal to 0, 1, 2, and 3. So we have S, P, D, F. So the d orbitals, there's 5 of them. They kind of look like this 4-leaf clover. And if you look at them, one of them's even got this crazy shape. It looks like a dumbbell with a donut kicking around it, okay? And you're like, well, and this is something I just want to talk. We got time. It's 10:26. We got time. Okay, if you're like, well, Mr. Dion, I can have an electron in any one of these, right? Yeah? Well, you see this electron that I've written here in green? There is 0 probability of finding an electron here. Okay, there is no probability, but sometimes the electron can be in that lobe where I've drawn it, and at other times it can be over here. Now you want to get your mind blown. Think about that. If you're like, well, how the heck did the electron get from here to here? I shouldn't be drawing arrows like that. That's heresy, isn't it? Okay, how did the electron get from here to here without passing through the middle? It doesn't. I can't explain it to you, but that's quantum mechanics. And in fact, it going through the region of 0 probability, I think that's called quantum tunneling. And I'm sure there's YouTube videos about that probably somebody has made. But anyhow, that's way beyond the scope of this class. But if you've ever wondered, like, well, hey, Mr. Dion, doesn't this orbital mean the electron? Like, you see the donut, this one here? You see I have the electron here? Well, how would the electron go from there, from the dumbbell, into the donut? From dumbbell to donuts, right? Well, it goes through this region of zero probability, but it doesn't, right? It just ends up in one or the other. Do you remember on Wednesday when I did my demonstration with the Apple Pencil? Close your eyes and open them. It's the same thing here, you guys, okay? I never claimed to be the guy that could explain it perfectly, but anyhow, some of you might be wondering, you know, what about F orbitals? Violet, it jumps, yeah. What about the shape of F orbitals? In case you're wondering, F orbitals have some really crazy shapes. Here they are. You got all kinds of dumbbells and donuts and dumbbells with dumbbells, and you know, so they have some really interesting shapes. There's a total of 7 of them, right? Because when we have L is equal to 3, right? That's an F orbital. We discussed that, and then we'd have -3, -2, -1, 0, +1, +2, and +3, right? Or you could do 2n plus, or yeah, 2l, 2l plus 1. Anyhow, either way, you end up with 7 total orbitals, and they're all shown here, okay? Anyhow, I'm never going to ask you to draw an F orbital, but in case you're curious, okay? And then if you look at the atomic orbitals for all the if you look at all the orbitals, I should say, and organize them by their shapes, you can see that here are some s orbitals right here. Those are all spheres, right? Those are all spheres here, and we go as we increase in principal quantum number from n is equal to 1 to 2 to 3 to 4 to 5 to 6 to 7, right? But then over here we have all these p orbitals over here, and you can see that at the top all we have are dumbbells, but then here we have a dumbbell within a dumbbell. Here we have a dumbbell within a dumbbell within a dumbbell, or as Gage would call it, a peanut within a peanut within a peanut within a peanut, so on and so forth. Okay, what else? Then you look over here, and we have the d orbitals, all shown here. Okay, and if you look at the shape of this, you know, this orbitron gallery of atomic orbitals, I'll just ask my students, does the shape of all the way these are organized remind you of anything that you've seen before in your life? The way these are organized, does it remind you of anything you've seen before in your travels? Maybe in university, maybe even in this class? Starts with P. Starts with, yes. Okay, sorry I didn't scroll down. Yeah. So the periodic table. All right. So somebody said, what shape should we memorize? You should know the shape of a p orbital and the shape of an s orbital, and you should know what a d orbital looks like for sure. So sp and d. You don't have to remember each one of them, what they're all called, the d orbitals, but you should know when you see one. You should be able to pick it out of a police lineup. Yeah, it looks like the periodic table. And so if I were to go to the periodic table, we're going to make the connection between the names of the orbitals, s, p, d, and f, and the regions that they're found in the periodic table when we get into our next chapter, or sorry, into our next lecture. Where are we anyway in this class? I want to be sure that I'm in the right spot here. Schedule, the schedule. Yeah, so on Monday, we're going to start talking about electron configuration, and we're really going to bring all of these concepts together, and we're going to come up with an even simpler way to account for every electron in an atom. All right, well, we've got 10 minutes left. Who wants to do just some plain old nothing but practice? Who wants to just do some practice? Me? Okay, yes, please. All right, thanks. I always appreciate polite students, Kenner. Me too. Let's just do some practice. You know, we spent a lot of time talking about theory. Let's get down to business. Aaron says I'm down. Well, I am too. Supply the missing quantum numbers and sublevel names. I'm going to give you guys a second to look at this one. See if you can figure it out. I'll give you 60 seconds. I'll take a drink of water. And Brittany, if you're wondering, like, what kind of questions do I have to be able to answer? This would be the type of question that you have to be able to answer, okay? These kinds of things. I'm not going to be asking for an essay about de Broglie. All right. Well, Kenner's got the first one, so why don't we just give it a shot? That wasn't 60 seconds, was it? Let me give you a few more seconds. All right, let's give it a go. Well, for the first one, A, if we have a 4p sublevel, that 4, that tells us our n, right? So that means that our n is going to be equal to 4. Now, L, remember when L is equal to 0, 1, 2, 3, that's an s orbital, a p orbital, a d orbital, and an f orbital. So if we have a p, right, that tells us that our L, that our L is going to be equal to 1. So we have a p orbital right there. Let's give the next one a shot. Who can tell me the name of B? What kind of orbital is B? Yes, excellent. Matthew, Kenner, Liv, excellent. It's a 2p orbital, right? Because we have n is equal to 2, we have L is equal to 1, right? And so that is going to be a 2p orbital. Let's give the next one the old college try here. We got n is equal to 3, L is equal to 2, ML is equal to minus 2. Well, the name of the orbital, if our n is equal to 3, it's going to be a 3. And if L is equal to 2, it's going to be a 2D, or sorry, a 3D. There we go. And we'll give the last one the old try. Oh boy, they didn't give us much information here, did they? Let's see. We got a 2D orbital. So that means that our n is going to be equal to 2, or sorry, a 2s orbital. When we have an s orbital, that means that L is equal to 0, and our only possible value of ML is 0. Let's see. Sorry. There we go. Thanks, Matthew. Thanks, everybody. Give me a thumbs up if you think you can solve that. Fill that table in. I bet you could. Probably faster than me. Right on. Okay. Well, let's move on. It says here, for each of the following, give the sublevel designation, not destination, designation, the allowable ML values, and the number of orbitals. Oh, jeepers. Let's do this one together. So remember, I always write this down for my students because sometimes they get confused. 0, 1, 2, 3. When L is equal to 0, that's an s orbital. When it's 1, it's a p orbital. When it's 2, it's a d orbital. When it's 3, it's an f orbital. And so if we have n is equal to 4 and L is equal to 2, this must be a 4d orbital. All right. So it's a 4d orbital. The ML values, okay, since L is equal to 2, remember that ML is equal to minus L all the way up to 0 to positive L. So ML is going to be equal to minus 2, minus 1, 0, plus 1, plus 2. And the number of orbitals. Well, every ML value is an orbital. And so I have a total of 5 orbitals. Right? So I have 5 orbitals. You could also use the equation 2L plus 1 is equal to 5. That works too. I don't use it a whole lot. I use it in my mind, but I don't teach it a ton. I just find it's easier to count up the orbitals, and that helps my students remember that ML represents orbitals. Let's give the next one a try. We get n is equal to 5, L is equal to 1. So this must be a 5p orbital. The values of ML when L is equal to 1 must be minus 1, 0, and positive 1. And that's a total of 3 orbitals because each ml value represents an orbital. The next one we have n is equal to 6, and we have L is equal to 3, so that's a 6f orbital. My values of ml will be -3, -2, -1, 0, +1, +2, and +3. That's a total of 7 orbitals when you add them all up. So we have 7 orbitals. All right. There we go. We got 3 minutes left. Let's see what we got here in the hopper. We already answered a question just like this one here. Here's just this is something that I stuck in here myself. I don't know if this is in the book, but this just shows you how we get the Rydberg equation from Bohr's equation. So if you're given either one, you can always solve for the other, right? So here I've given you Bohr's equation, and then you know this formula, right? We've talked about this several times on Wednesday and today. And so if you want to solve for 1 over lambda, right, you would just plug in this number and divide it by h over c, and then you end up with this number here, okay? So all I have to do, so my take-home message from this slide is really all I have to do is either give you this equation or give you this equation, 1 over wavelength is equal to this. Either one, and you can solve for the other. All right, I feel like we've covered a lot of ground. And if you're the kind of person, which I'm sure most of my students are like this, and this isn't a judgment, but I bet you that most people who felt like they enjoyed the second half of the lecture more than the first half of the lecture. Did anybody feel that way? Like they're like, oh, the second half of the lecture made more sense to me. Because if you felt that way, it's not uncommon. Not uncommon at all. Well, let me tell you right now, 99% of the questions that I'll ask you from this chapter will be based on the second half of the lecture, okay? Yeah, like Brittany says, it all comes together, right? That's why, and I kind of warned you about that at the beginning, I do spend a little bit of time yammering on about de Broglie and uncertainty and all those kinds of things. And in fact, I think there's even a problem in there that we didn't solve. Shoot, now that I think about it, we didn't solve the problem about the uncertainty, did we? I think there was a problem in there that I missed. Uh-oh, Mr. Dion, I'm losing it. Which question was it? Sorry, guys, I'm going overtime here probably. It was question, I thought I had a question in there about uncertainty, didn't I? No, maybe I didn't. No, maybe I did. Maybe I did at one time and I took it out or something. Anyhow. No, I guess I covered everything. Sorry. I am losing it. It's Friday. All right. Well, what's our plan? If I was you, I would be sure to get my Learn Smart for Chapter 8 done right away. I would be doing some practice problems from the book. Could be doing the homework. There's so many places to access problems nowadays. And I would try to read as much as I can of the Chapter 8 before coming to class. And I think, you know what? I'm going to stop recording because I don't want a record of this.